Hello students, this is Mr. Allen. Today I'm going to be sharing with you lesson 4.3, which is on Riemann sums. I just want to let you know that this lesson is one of the more technical. I have lots of things already actually typed into the lesson to kind of speed up this process because I want to limit this to as close to 10 minutes as possible. And I also typed it in so that it would be very easy for you to see. So our objectives here is to understand the definition of a Riemann sum, evaluate definite integrals using limits, and evaluate definite integrals using properties. So I'm going to do this very first example quickly. I just want to highlight some things. So let's say that I am wanting to find the area under the function, the square root of x from 0 to 1, and the x-axis. In other words, I'm looking for this area here. Okay. If you recall from last year, we had something that looked like this. Limit as n goes to infinity of the sum of f of c sub I delta x sub I. This is the formula that got us the area. It should be noted that the intervals do not have to be equal, but in practice we typically do make them equal. So first of all, probably to get things started, how do we find the delta x sub i's? Well, in this example, we're starting at x, we're going from 0 to 1. So to find the change in the x sub i's, we're going to do the following. We're going to do, this is 0 here, and then this is at 1. So we're going to do I squared over n squared minus the quantity I minus 1 squared over n squared. We can simplify this using the binomial expansion rule and then distributing the negative I. We notice they have the common denominator. So we get this. This is going to be our delta x sub I. Now we can plug that information into our problem. This is the result from the previous slide. Here's our x sub I. We are plugging I squared over n squared. And you might be asking yourself, why is it I squared over n squared? I'm just letting you know this is remember this, we're dealing with the square root function here. This is a more complicated example than the linear ones we did last year. So now what we're going to do is we're going to use the limit process to evaluate this Riemann sum. So this gives us the limit as n goes to infinity. Now, when you do the square root of n squared, that's going to give you just n, and then we have an n squared, so that's why that's n to the third there and not n to the fourth. We clean up the numerator, we get this. Now we've got to use our rules. We want to get rid of the sum of this I squared and the sum of this I. So the rule for the sum of I is n times n plus 1 over 2. That was one of those formulas we used last year. And then this I squared is n times the quantity n plus 1 times the quantity 2n plus 1 over 6. Now we're just going to do some algebra to figure out what this limit is. At this point here, we should recognize that we have the limit of a rational function with the same power in the numerator and the denominator. So it's simply the ratio of their lead coefficients. So we get the limit as 2/3. In other words, the area under this curve is 2/3 from 0 to 1. Here's our definition of a Riemann sum. I'm not going to read this to you. Again, I want to kind of keep this as short and sweet as possible, but this is our Riemann sum. It is a sum of f of c sub I times delta x sub I. Remember, these are going to give us the heights of each rectangle. This is going to give us the width of each rectangle, and then we can calculate those individual areas and then sum them all together. The width of the largest subinterval, delta, is the norm. So this is called the norm of our regular partition. That's how we'll write that. This is equivalent to delta x. And the formula that we're going to use for that is b minus a over n. So this formula is pretty handy to know. So delta x is equal to, and b is the ending x value, and a is the starting x value. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches 0. In other words, the norm of delta goes to 0 implies that n is going to infinity. So as we take the norm of the partitions to 0, the number of rectangles, if you will, is going to infinity. To define the definite integral, consider the following limit. So again, this is a definite integral. Now, if we throw a limit in front of that involving the norm, this is how we're going to get to our definite integral. And here is the definition of a definite integral. Again, I'm going to just kind of highlight this. Here is the key idea. Our Riemann sum, if we do the limit of that as the norm goes to 0, that is our definite integral. And remember, this is what we want to get to, and we'll talk more about the shortcuts later. Okay? The A is called the lower limit of integration. The B is called the upper limit. This is referred to completely as a definite integral. This is kind of an important theorem. It basically says this: if a function is continuous on a closed interval, then you can integrate it. You can integrate on that closed interval. So continuity implies integrability. So let's look at an example of a definite integral. So I'm trying to find what is the definite integral from -2 to 1 of 2x dx. So we're going to go ahead and start looking at this. For a computational convenience, we're going to let delta, by subdividing the interval -2 to 1 into n subintervals of equal length. So that's going to tell us that our delta x sub I, which is the same thing as delta x, we're going to use our formula here again, and that's b minus a over n. So what's the difference between those two guys? It's 3 over n. Now to find our c sub I, we're just going to do our a value. That's where we start. And then we're going to do I times our delta x. So in this case, we're starting at -2. So it's -2 plus 3i over n. So our definite integral is equal to this limit of a Riemann sum. And that could then be changed into the following. And this is most of the time, this is the way you will see me write our definite integrals. I kind of skip over that step, but technically that's what you need to do. All right, so now we're going to just substitute some things in, and let me go ahead and clear everything off there so you can see that. So now, as I'm going to do is we figured out what our c sub I is. We figured out what our delta x is. 2 here is because of the 2 right there. So now we're going to clean this up a little bit. So notice that one of the 6 and the n's will come out in the front. And then we clean this up further. Remember, our formula for I is as follows. So then we've got the 3 in here. And now we're going to take n to infinity. And of course, this should be easy to see that this final answer is going to be -3. Now, guys, I whizzed through that. If I was writing this down, that would have taken me several minutes to do. And as you may remember from last year, doing all of that process, it's easy to make a mistake. This one's a pretty simple one because it was just a linear function here. The answer was -3, which tells us the area of these rectangles over here was more than the area of the rectangles up above the x-axis, so that's why it was negative. Definite integrals can be positive, negative, or 0. Area cannot be negative, but a definite integral can be negative, and that's just, it depends on the application that you're looking at. Okay, theorem 4.5 basically tells us that area can be equivalent to a definite integral. As an example of this theorem, consider the function 4x minus x squared. If I want to find the area under this curve, I am simply going to evaluate the definite integral from 0 to 4. Now, example 3, I'm going to, this is different than the previous example we've done here. I'm not going to tell you the answer. You can figure that out on your own with a calculator or do it by hand. One of the things before we actually worked in a whole lot with the fundamental theorem of calculus, which we'll get to in the next video, is areas of common geometric figures. So I claim that in fact, I did this last year, you can find the value of these definite integrals without actually knowing how to do integration. So for example, this first integral, if I want to find the area under that curve, well, it's just the line y equals 4, so I'm just going from 1 to 3. So what would be the area there? Well, 2 times 4 or 8. That doesn't require you to know how to integrate, but that's what it is, and you could actually integrate it and find that that is true. We could do the same thing here. Here, though, instead of it being a constant function, it was linear, so you could find the area of a trapezoid. You'd find the answer here is 10.5. Here we have a semicircle. Even though this function looks much more complicated, it's half of a circle. How do we find the area of a circle? Well, it's pi r squared, but we got to do half of it. So this area is going to be 2 pi. And guys, I apologize. We are right at 10 minutes, but I do have just a little bit more to do here, and that's involving the properties. Okay, there are several properties. I'm going to buzz through them very quickly. Remember, if we integrate from a to a, that's 0. If you do the integral from b to a and then you switch it to a to b, then you have to do the opposite. This is probably the one that students tend to forget the most. This one's pretty, I think, self-explanatory. You're integrating from a to a, it's just 0. Here is the additive property. So if I'm integrating from a to b and it turns out that c is between a and b, well, then I can integrate from a to c first and then from c to b. In other words, you can break it into pieces. Here are a couple more properties. This is the constant multiplier property. In other words, this k can come to the front. And again, sum and difference rule holds as well. Let's rip through the last example here and wind this up. So how could I find the value? Now, you guys could calculate this by hand, but we could use the properties before we actually knew the fundamental theorem of calculus. We're given that the integral from 1 to 3 of x squared is this, and the integral of x from 1 to 3 is that, and the integral from 1 to 3 of dx is that. So the integral of the whole thing can be broken using the addition property into the following. And then I could pull out this negative, I could pull out the 4, I could pull out the negative 3, and then I could just substitute the information in that we know, and we'll get our final answer here of 4/3. That brings us to the end. We're at 12 minutes. Sorry, I tried my best to keep it under 10.